Rolle's theorem. Assume that f of x is continuous on the closed interval from a to b and differentiable on the open interval from a to b. So same hypothesis as the mean value theorem. If f of a equals f of b, so let's stop right there. That's a third component to the hypothesis. So I need a function that's continuous on a closed interval. So on this graph, I'm going to say this is the graph of f of x here. And I'm going to say my closed interval goes from -4 to 4. So closed interval, I have my closed endpoints. It's differentiable on the open interval, so no cusps, corners, or vertical tangents. And f of a equals f of b. This part means the y values at the endpoints are the same. At the endpoints, I'll put match. So they're the exact same y value at the endpoint. So here at -4, my y value is also -4. And at +4, my y value is also -4. So f of -4 equals f of 4. All three parts of the hypothesis are satisfied. So then there exists a number c between a and b such that f prime of c equals 0. So if we have continuity, differentiability, and the y values of the endpoints are the same, then there has to be a place where the derivative somewhere between a and b has to equal 0. So the slope of the tangent line has to equal 0. So the slope of the tangent line equals 0 at the x value 0 here, which falls between -4 and 4, my endpoints. So there was some place where the slope of the tangent line equals 0. Now here's something that I want to point out, is that if we were to connect the two endpoints together here to find the slope of the secant line, this would be a horizontal line with slope 0. So it turns out that in fact, Rolle's theorem is a special case of the mean value theorem. It's just that this 0 here is f of b minus f of a over b minus a. So f of b and f of a are the same value. F of a equals f of b. So that forces the top of this to equal 0. And 0 over some number equals 0. So Rolle's theorem is really just the mean value theorem. So I have that extra part to the hypothesis that if the two y values of the endpoints are the same, that there's going to be a place where the derivative equals 0, because that's the slope of the secant line. The slope of the secant line will also be 0. Alright, so before we move on to examples, I want to reiterate a really important point, that Rolle's theorem is just a special case of the mean value theorem when f of a equals f of b. So this image on the left corresponded to the mean value theorem graphical interpretation. So if I have that interval from a to b where I'm continuous and differentiable, then there's some place c where the slope of the tangent line is equal to the slope of the secant line between the two endpoints. So this graphical representation of Rolle's theorem shows f of a equal to f of b, so that the slope of the secant line is horizontal, so there must be a place between a and b, c, such that the derivative at c is 0, so that the slope of the tangent line at c is horizontal. Alright, in this first example, does Rolle's theorem apply for f of x equals x to the fourth minus x squared on -2 to 2? So does Rolle's theorem apply means do we satisfy the hypothesis of Rolle's theorem? So this is a polynomial. It's continuous and differentiable everywhere. So I know f of x is differentiable and continuous. But in order to satisfy Rolle's theorem, I need that extra special condition that the endpoint function values have to be the same. So does f of -2 equal f of 2? That's what I'm checking. So if I were to substitute in -2, I'll get -2 to the fourth minus -2 squared. So -2 to the fourth is 16 minus 4, so I get out 12. And is that the same as substituting in 2? Well, since I'm raising them to even exponents, I am going to get 16 minus 4, so I will get 12 again. So yes, I can erase the question mark. F of x is differentiable and continuous, and f of -2 equals f of 2, so Rolle's theorem applies. So there's going to be some value c between -2 and 2 such that the slope of the tangent line equals 0. Alright, in this next example, the following table represents a function f of x that is differentiable everywhere. Does the graph of f of x have at least one horizontal tangent line? Explain. So I have this function that's differentiable, so it's continuous, so I've satisfied that portion of Rolle's theorem. I know that I have to satisfy Rolle's theorem because the question is asking me if f of x has a horizontal tangent line. So this portion right here is like asking, is there some place where f prime of x equals 0? They're equivalent statements. So it's translating this horizontal tangent line to understanding that that means when the derivative is equal to 0. Well, so when I'm given information about f of x and I want to know whether f prime of x equals 0, I need to make sure I have differentiability, continuity, but I need two y values to be the same. So when looking at this table of data, I can see that when I substitute in 1, I get out -2, and when I substitute in 4, I get out -2. So since f is differentiable and continuous, and since f of 1 equals f of 4, so they are the same value, they are both -2, by Rolle's theorem, I'm going to abbreviate theorem as THM, there is some c in the interval from 1 to 4. So there's some c value, remember c comes from the x-axis, so there's some c between 1 and 4 such that f prime of c equals 0. So since f is differentiable and continuous, and because the two endpoints are, or the two y values of the endpoints are the same value, Rolle's theorem guarantees that there's some c value between 1 and 4 such that f prime of c equals 0. Or in other words, there's a horizontal tangent line. We have a horizontal tan line. So we could have just said there is some c such that there is a horizontal tangent line at C. Again, there's a lot of different wording that is okay. It's understanding the concept. So I hate to say you have to structure it in this one particular way, because it's really about just explaining that there is going to be guaranteed some value by Rolle's theorem where the derivative is 0. If the derivative is 0, there's going to be a horizontal tangent line there. Alright, in this next example, the following represents the position of a particle in inches where time is in seconds. Note that S of t is differentiable everywhere. So here's this table of data, and in the first question we're asked, what's the minimum number of times the particle is at 4 inches? So taking a closer look at the table, at time 0, the particle is at 2 inches. At time 1, it's at 3 inches. At time 3, it's at 5 inches. At time 4, it's back to 3 inches. And then at time 6, it jumped to 7 inches. So between 1 and 3, at some time between 1 and 3, the particle had to have been 4 inches. And this is by the intermediate value theorem. So because this is a differentiable function, it is continuous. So since S is differentiable, it's continuous. Now, by the intermediate value theorem, 4 falls between 3 different intervals, actually. It falls between the interval from 1 to 3, from 3 to 4, and from 4 to 6. Over those time intervals, the position is going to have to be 4 inches. So by IVT, since, and we have 3 different situations happening, since 4 is between S of 1 and S of 3, so S of 1 is 3 and S of 3 is 5, so 4 is in this interval. 4 is also in the interval from 3 to 4, but I have to be careful about the way I write it right now, because 4 is greater than S of 4, because S of 4 is 3, and 4 is less than S of 3. So I need to make sure the order is correct, because S of 4, this number right here, is 3, and S of 3 is 5. So 4 is between 3 and 5. So 3 is less than 4 is less than 5 is what that second statement says. And then the last statement that I'm going to need to write is that S of 4 is less than 4 is less than S of 6. So 4 falls between these 3 intervals. So by the IVT, since all 3 of these are true, there is at least 3 times the object or particle, I guess I should have said, is at 4 inches. So I definitely don't recommend really always graphing this information, but on this particular example, I'm going to do a quick little graph to kind of explain why it's the least number of times. So if this is my t-axis for time and this is my s of t-axis for the position in inches, at time 0, I'm right here at 2, and at time 1, I'm up here at 3. At 3, I went up to 5. At 4, I dropped back down to 3. And then way over here at 6, I jumped up to 7. Now, because this function is differentiable, it's also continuous. So even though I can't officially connect the dots together, I do know that the dots do connect together. So I don't know exactly how they connect, but I know they connect. So between 0 and 1, I have to go from 2 to 3. Well, going from 2 to 3 doesn't ever mean I have to cross the value 4. So it's like asking, what's the minimum number of times I have to cross this horizontal line? Well, going from 1 to 3 on the t-axis means I have to get from 3 to 5 on the s of t, or the vertical axis, so I'm going to have to cross 4 once here. Then to get back down, I'm going to have to cross again. And then to get back up to 7, I'm going to have to cross a third time. So I had crossing 1, 2, 3 times at a minimum. But who's to say, since I can't officially connect these, that between 1 and 3, the graph didn't do this craziness and cross 5 or 6 different times. So that's why this is the minimum number of times the particle is at 4 inches. So now, part B. Is the particle ever at rest? Explain. So a particle is at rest, or an object is at rest, when velocity equals 0. Well, velocity is s prime of t, and I want to make that connection because I'm only given information about s of t. So now this is going to be my application of Rolle's theorem. So when I see a derivative being 0, if I can show that the original function had 2 y values that are the same, because I have differentiable and continuous, then I can say that there's some place where the derivative is 0. So my explanation is, since, again, f is differentiable and continuous, and I'm going to need 2 y values that are the same. So I have that. I have at s of 1 and s of 4, so since f is differentiable and continuous and s of 1 equals s of 4, they're both 3. By Rolle's theorem, abbreviate theorem, there must be, or there is, some t on the interval from 1 to 4, so time comes from the values 1 to 4, such that s prime of t equals 0. And we have to remember s prime of t is the same as v of t. So is the particle ever at rest? So since f is differentiable and continuous and s of 1 equals s of 4 equals 3, by Rolle's theorem there is some t in 1 to 4 such that s prime of t equals 0. So yes, the particle is at rest. The particle is at rest. So I want to make sure and answer the question formally in my explanation. So I would have to state all of this in order to use Rolle's theorem, that I satisfy all parts of the hypothesis, and this is key. In all of these problems where I have to use a table of data, it's important that I identify the correct intervals to show what I want to happen, where exactly it actually happened.